In the last lecture, we considered Cauchy problems for Burger's equation where the Cauchy data or the initial data was not smooth, or even when the initial data was smooth, we found that in one of the examples that solution is only piecewise smooth. So, such functions cannot be solutions in the usual sense which we described as classical solutions. So, we ask the question, is there a framework under which we can admit such functions also as solutions to Burger's equation and in general for a first order partial differential equation. So, we look into that in this lecture. So, do not be afraid by the word conservation laws, we are not going to study too much about it. It is only in the context of Burger's equation that we are going to discuss. Burger's equation can be written in what is called a conservative form, we will come to that. So, this is a brief recall from the last lecture. We considered 4 initial value problems for Burger's equation. We came across 2 kinds of difficulties. First one was a solution could not be determined in some region of the upper half plane because there were no base characteristics, and a solution becomes multivalued due to too many base characteristics entering a particular region. That is another reason why we could not define what is a solution there. There was some ambiguity. So, the notion of solution we considered so far prior to the Burger's equation is often called classical solution. As a consequence, initial value problems do not admit global solutions. We already understood that. If we relax the notion of solution, then initial value problems may admit global solutions. That possibility we will get. A relaxed notion of solution is possible for Burger's equation due to its conservative form, which is given by ut plus u square by 2. This bracket x stands for dou by dou x, differentiation with respect to x. So, assuming u is smooth, when you do expand this by chain rule, what you get is ut plus ux equal to 0. Okay, we have used uy when we solved it by characteristics method, and but I told you that y has the interpretation of time. So, therefore, it is ut, this is fine. Okay. The relaxed notion is very natural for equations in conservative form. We are going to introduce one relaxed notion. Of course, conservation laws are not new to us, we have seen them already in traffic modeling. So, this notion is called generalized notion that we are talking about is called, or relaxed notion is called weak solutions to conservation laws. So, there is a guideline for relaxing the notion of a solution. Even for a conservation law, we can demand that it should be a nice function, differentiable function. So, that ut plus u square by 2 differentiation with respect to x equal to 0 is actually ut plus ux equal to 0. Okay. But we want to admit functions which are not so much smooth as solutions. Therefore, we would like to define a new concept of a relaxed solution, and there should be some guidelines. What are those? 3 requirements are there. Any notion of relaxed solution, okay, we may call it weak solution, must have the following 3 properties. What are they? Any smooth solution should also be a weak solution. Okay, this is to be expected. It should be there, right? Otherwise, you are defining some new solution. Earlier we said we want to relax because some equations may not have the smooth solutions or a classical solutions, but if they do have classical solution, we would like that the relaxed notion also it admits as a solution. Therefore, smooth solution should also be a weak solution. This is usually the guiding factor in defining any notion of weak solution. We will soon see how that is going to be done. And any weak solution, if it is smooth, then it should be classical solution. This is a second requirement, of course. So, we prove that the notion of a relaxed solution which we are going to give motivated by 1. So, we are going to define what is called a relaxed solution or a weak solution concept, and then we show that any smooth solution is a weak solution, and then we also show that any weak solution which is smooth is actually a classical solution. We will show that. These are the two, and then the third one is the most important thing, and we are not going to address that. Any reasonable problem should have a weak solution. Otherwise, what is the use of a notion of a solution when you can't show that such a solution exists when the problem is reasonable, right? I am not expanding what is reasonable, but this is what one has to remember. These are guidelines. Discussion of this requirement for the notion of weak solution we are not going to do, that is beyond the scope of the course. So, let us look at the initial value problem for a conservation law. Burger's equation in the conservative form is a special example of this, where f is u, f of u is u, g of u is u square by 2. So, assume that this equation has a classical solution, that means a differentiable solution. So, that this you can expand f dash u into u y, g dash u into u x equal to 0 by chain rule, and u x 0 equal to h x. This u of x 0 makes sense and is equal to a pre-assigned h x. So, here f, g and h are a priori given to you, smooth functions. So, let us see how we arrive at a notion of weak solution. First thing is to take a function phi which is compactly supported in this domain R cross closed interval 0 infinity closed at 0 and C infinity, that is it is differentiable any number of times. C infinity function with compact support and the domain is R cross 0 infinity 0 closed. And first thing is your equation you have to multiply with phi. This equation is multiplied with phi and integrate. So, this equation is simply this equation multiplied with phi, the two terms are separated, and integrate on your domain R cross 0 infinity. Okay. So, what have we achieved? Nothing. We have not yet relaxed that u can be a lesser smooth function, right, for non-differential function, etc. Therefore, first thing, the moment we see a derivative here and a derivative here, first thing is idea is to shift this derivative to C infinity function that we have. So, therefore, we have to do integration by parts, in this integral with respect to y, in this integral with respect to x. So, with that we get, from here we get this integral, and from here when we do we get this integral, and in this integral there is a one boundary term which is here, because we are taking phi which are compactly supported in closed 0 infinity, not open 0 infinity. If it is open 0 infinity, this term will not be there because phi x 0 will be 0 in that case, but we are taking with this. That is because we want to account for the initial condition, that is what is going to come here. So, this is what you get at the end of integration by parts. So, what we observed just now is that any classical solution satisfies this integral equation, and for every phi which is C 0 infinity R cross 0 infinity. And this equation, if you see, it is meaningful even for u which are not C1. For example, u is only continuous, f of u makes sense, right, f of h of x of course makes sense, g of u makes sense, and these integrals are on infinite domains, but phi is having compact support. So, essentially the integrals are on a bounded set. Therefore, when you integrate continuous functions and bounded sets, it is integrable. These are well defined integrals. Okay. So, therefore, this is meaningful even for u which are not C1. I just use the word u is continuous, of course, you do not need even u to be continuous, what all you need is this should make sense. A notion of weak solution gets defined once we mention what kind of functions u we would like to allow them as solutions. So, we have to decide which u you are going to allow as solutions for your problem, then a notion gets defined. You will ask that this integral equation should be satisfied for all phi in this space, and u should lie in some space, that you have to identify, you have to decide. So, you fix the class of function that you are interested in or you like, with the only condition that this equation is satisfied for every phi. You will get a notion of weak solution. So, let us give one notion of weak solution here. Assume that H is L infinity of R, this log should not be there because L infinity functions are bounded functions. Or if I put L infinity log of R, it just means that it is bounded function on every compact set, that is good enough. So, L infinity log is good, we can keep this. L infinity just means that Lebesgue measurable functions which are bounded, essentially bounded functions. Whenever there is a log, it means that on compact sets some property holds. L infinity log means it is in L infinity of every compact subset of R. Now, U in L infinity log of this set, see now we just want bounded measurable functions as solutions, not even bounded everywhere, bounded on every compact set, that is good enough for this notion. In particular, non-differentiable functions, all of them will come under this, they satisfy this condition. So, U in L infinity log is said to be a weak solution of the initial value problem, which is here, if for every phi C0 infinity this integral equation is satisfied. Okay. This was first of all derived from this equation, assuming that you use a smooth solution multiplied with a phi coming from this space, and then we found this is satisfied. Now, we forget all that and we say as long as this is satisfied I am happy, and now I put some conditions so that this makes sense, and we are demanding it should be equal to 0. One such class is L infinity log R cross 0 infinity. Okay, the previous definition, if we restrict phi to compactly supported functions infinitely many times differentiable R cross open 0 infinity, then the boundary integral, the integral on R will vanish, it will be 0, as I pointed out phi of x0 is 0. So, we are left with only these two terms. Then U is called a weak solution to the conservation law, not Cauchy problem for the conservation law, but weak solution to the conservation law. That means, we are worried only about the equation and not the initial conditions. The notion of a weak solution to the initial value problem is also referred to as its weak formulation. That integral equation which we saw on the previous slide is often called the weak formulation of the conservation law. Now, this is what we have finished the guiding principle part 1, all smooth solutions should satisfy the new formulation, that is how we have derived. Now, we will go to step 2, where we are going to show if you have a weak solution and it is smooth, it must be classical solution. That is what we are going to establish now. So, for this we need to assume slightly one extra condition on f. Of course, for Burger's equation f of u is u, of course that is a 1 function. So, let f be a 1 function, let u be a smooth function, that is C1, because it is a first order PDE, C1 is required, and here I put continuity up to 0, that means u of x0 makes sense. If you have continuity up to this 0, close 0, that means that u of x comma 0 makes sense. Suppose this is a weak solution to the initial value problem, then u is a classical solution of the initial value problem. Okay, that is the conclusion. So, here we are assuming u is a weak solution and smooth, then we are going to say it is a classical solution of the initial value problem. So, since u is a weak solution and also smooth, what does it mean? I can go back, the strongness and the weakness, what is the connection? Integration by parts. So, I need to do integration, reverse integration by parts from the weak formulation. So, this is the meaning of what we have. Here it is a weak solution to the conservation law. Now, if you do integration by parts, you will get back this. Okay, this is the boundary term that is going to come. So, what happens if I take a phi which is C0 infinity open 0 infinity, this term will not be there. We will get this. Since the integrand is continuous, right, integrand is continuous and phi is C0 infinity is arbitrary, fundamental lemma in calculus of variation. Essentially it means if you integrate against C0 infinity function, a certain function, and you always get 0, then that function must be 0. So, it is essentially like this. Just imagine something like this. We have phi psi equal to 0 for all phi in C0 infinity functions omega, that would imply that psi is 0. Under various assumptions psi it is true, definitely when psi is continuous it is true. So, therefore, use a solution to the conservation law. Since use a solution to the conservation law, this equation now just becomes the last term, because these two together are 0. So, we have this. Now, once again phi is arbitrary, therefore, this must be equal to this, and if the function f is 1 1, inside thing must be equal to inside thing, that is the idea. So, this is true for every phi in C0 infinity r cross close 0 infinity. Now, any if you notice, this is only function of x here, this is only function of x, it is not like y, there is no y, it is just function of x, integral is an r. So, we can get any smooth function C0 infinity function of r through this phi. Okay. Any psi in C0 infinity r looks like phi of x0 for some phi here. For example, phi of xy equal to psi x into chi y, where chi is psi is C0 infinity r, that is given to you, and chi is C0 infinity of close 0 infinity with chi identically equal to 1 in some interval 0 1. So, when you put y equal to 0, chi of 0 is 1, therefore, you get psi of x. So, that is simply this. Now, once again you apply this, is a continuous function, integrate against any C0 infinity of r function is 0, then this function must be 0. That result I am loosely calling it as fundamental lemma in calculus of variations. So, using that f is a 1 1 function, we get ux0 equal to hx. Otherwise, to start with you get f of ux0 equal to f of hx. Since f is 1 1, you can take away the f and you get ux0 equal to hx. Now, we are going to look at another question, which piecewise smooth functions are not weak solutions. The following theorem will be helpful in deciding that. Suppose you have a set D subset of r cross 0 infinity, and suppose you have a curve that divides D into two parts. So, generally one writes this kind of picture, this is D and you have a curve gamma, and it cuts you this into two pieces D1 and D2. And suppose U1 is C1 and continuous up to the boundary, D1 closure means up to boundary. That means U1 is here, it is smooth, similarly U2 is here. So, U1 is C1 of D1 and also continuous up to the boundary. So, that I want to talk about the values of U1 on gamma. Similarly, I want to talk about U2, values of U2 on gamma. So, I will require C1 of D2 and continuous up to D2 closure. So, that U2 on gamma is also meaningful. So, two conditions generally people write as an intersection. So, this and U2 is C1 in the second domain and continuous up to its closure. Define a function u on D now like this, U1 in D1, U2 in D2. Okay, on gamma we are not defining. Now, let this bracket u denote the jump in the values of u across gamma. That means, we had this is D, we had D1 here, D2 here. Now, U1 on gamma makes sense at points of gamma, similarly U2 on gamma makes sense. So, we can look at the jump U2 at a point P on gamma minus U1 at the point P. This is the jump. jump in u at the point P. You could also define u1 minus u2 at point P. I have used u2 minus u1, both are same. You have to have just a consistent way of defining it. So, this is the definition. At any point xy which is on gamma, you define the jump in u as u2 minus u1 at that point. So, we have defined what is the jump at all points on gamma. Now, similarly you define fu, jump in fu and jump in gu. Okay. Jump in fu at a point P is f of u2 at P minus f of u1 at P. That should be the definition. Jump in f of u at a point P is on D2 the value is going to be u2, right, f of u2 at P minus f of u1 at P. That is the jump. Similarly, jump in G is also defined. Then the following statements are equivalent. Saying that u is a weak solution to the conservation law is same as saying that u1 and u2 are classical solutions in the of the conservation law in both the domains D1 and D2, u1 in D1 and u2 in D2, and along the curve gamma certain condition holds which is fu ny plus gu nx equal to 0. What is nx ny? It denotes the unit outward normal to gamma. That means we had like that, we had a gamma, take a point, so normal direction. This is tangential direction, this is a normal direction. You can take either this or this, any one of them you choose, does not matter, that is what we are saying. So, let us choose for example this, does not matter, because the equation anyway is equal to 0. If you replace nx ny with minus nx minus ny, it is the same. Okay. So, further if the curve is described by x equal to xy, there is an interesting assumption. It is given by x equal to xy y. What does it mean? The curve looks like xy of y comma y. Okay, that means it is a graph with respect to the y variable. Then the Rankine-Hugoniot condition takes this form dz by dy equal to jump in G by jump in f. What is the importance of a curve given by x equal to xy y? See, y is a time variable, right? Y is time variable. So, it is like xi of t, right, x equal to xi of t. It is giving you some points in x which are the values of somebody at t. So, it is telling you the location of somebody as time evolves. So, when y is time variable, the curve tracks the location of points. If the initial data is an x axis, it will track the location of the points from x axis. Tracking points of discontinuity or non-differentiability of the initial data, where ux0 is hx, hx is the initial condition. So, these kind of things can be tracked by this curve. That is why we always assume x equal to xi y. So, proof of 1 implies 2. In the definition of the weak solution to the conservation law, using phi, I am allowed to use any phi which is C0 infinity of d, right. Now, I use C0 infinity of d1 and d2. We get the first part, that is it is a smooth solution, it is a solution because of smoothness we do integration by parts. Now, let us derive the Rankine-Hugoniot condition along points of gamma. So, take a phi which is C0 infinity of d, now I can't do di, if I take di I am ignoring the other di, right. If I take d1 C0 infinity of d1 I am forgetting d2, no, because the jumps are across gamma, gamma is there for both d1 and d2, right, it is a boundary. So, therefore, you take a C0 infinity of d and the weak formulation of the conservation law reduces to this, and since d is a disjoint union, you write this integral as integral over d1 plus integral over d2. Okay. Now, I think we have to do integration by parts. So, if nx ny denote unit outward normal to d1, then minus nx minus ny denotes unit outward normal to d2, because this unit outward normal is what appears in integration by parts. So, performing integration by parts, we get these terms. Dou by dou I has gone to on D1 u is u1, u is u1 on D1. Similarly, here u is u2 on D2, u is u2 on D2. That is why you get fu1y from here, gu1x from here, and this is the boundary term coming from this integral. Okay, one with respect to x, one with respect to y. So, this is the other one. Or you can also treat this as a Green's theorem. Okay, this is okay. I will leave it to you. We call integration by parts by various names depending on the context. Fine. U1 and U2 are classical solutions to conservation law. We already proved. Therefore, some things will be 0. Okay, the domain integrals will go off. What remains is a gamma integral. Okay, this is what you have now. The notation nx ny is fixed. Okay, nx ny is outward normal to D1. Then we have used that minus nx minus ny is outward unit normal to D2 while doing integration by parts. So, finally, we end up with this gamma integral. Now, phi is arbitrary, therefore, integrand must be 0, and which will give you Rankine-Hugoniot condition. If the curve is given by x equal to xi y, we compute the normal direction is 1 comma minus d xi by dy. Therefore, Rankine-Hugoniot condition becomes this equation, d xi by dy is jump in g by jump in f. 2 implies 1 is very simple, so that is left as an exercise. A few remarks on the last theorem. We already started with this remark when we stated the theorem. The curve gamma described by x equal to xi y for some function xi. This means that gamma is the graph of a function of y. The curve gamma is a curve of discontinuity for weak solution. In Burger's equation, the variable y has the interpretation of time variable, and thus y going to xi y tracks the location of discontinuity from its initial location as the time evolves. So, theorem is useful in rejecting the candidature of a piecewise smooth function for a weak solution to IVP. How? You simply show that Rankine-Hugoniot condition is not satisfied along the discontinuity curve, and therefore, it cannot be a weak solution. So, it is useful in rejecting the candidature. Theorem analyzed solutions with jumps across one curve. Why not consider functions with jumps across more than one curve? Very natural question. It is important while dealing with initial profiles which have more than one point of non-smoothness. Theorem is applicable along every curve of discontinuity as long as the functions considered are piecewise smooth functions. Caution is there exists multiple conservative forms, multiple. Okay. For Burger's equation, we have written 1, right, uy plus u square by 2 of x equal to 0, and these are so many as natural numbers. So, we have here at least infinitely many are there. Now, which one will you consider? You have to decide. So, note that RH condition also depends on k, because it is jump in g by jump in f, that is the equation for dz by dy. Now, g varies, this is the g, new g, right, it depends on k. Similarly, this is f, depends on k. So, RH condition depends on k. So, what does that mean? If you take two different k's and take u and v which are weak solutions corresponding to the different k's, then the vice versa may not be true. So, therefore, in applications you have to realize which one is the most correct or useful conservative form of your equation also. So, weak solutions are not unique, because we have relaxed the notion of solution. Now, lot more functions, we do not expect uniqueness now, that is what is demonstrated by these examples. Now, we are going to use the following conservative form throughout this lecture from now onwards: uy plus u square by 2 x equal to 0. Let us write down what is the Rankine-Hugoniot condition. It will turn out to be u1 at point of gamma plus u2 at the point of gamma by 2, that means the average of u1 and u2. So, for example, this is the one d1, d2, u1 here, u2 here, take a point, take the value of u1 and take the value of u2 and take the average. That should be the dxi by dy, the slope with respect to y here. Okay. This is the example 1 that we considered in the last lecture with initial data -1 and 1, -1 up to x less than 0, 1 for x greater than or equal to 0. It has many weak solutions, few of them are being given here. For example, here we have two curves of discontinuity, one is the line x equal to -y, another one is the line x equal to y. Now let us see whether our RH condition is satisfied here. What is the average of u1 and this is d1, this is d2 here. So, u1 and u2 average, x by y on this line is -1 because the line itself is x equal to -y, therefore, x by y is -1. Therefore, what is the average of -1 and -1? It is -1. So, x equal to xi y, that is the curve we are considering, and we have to look at dxi by dy. So, in this example dxi by dy is -1 and which is also equal to the average. Therefore, RH condition is satisfied across this line. Now, let us discuss across this line. Across this line, one side the value is 1, other side is x by y, but on this line x by y is 1. Therefore, average is 1 and that is same as x equal to xi y, derivative of xi is 1. So, Rankine-Hugoniot condition is also satisfied across this line. Therefore, this is a weak solution. Let us look at this. Here the curve of discontinuity is x equal to xi of y equal to 0. So, therefore, dxi by dy of course is 0 and that is same as the average of -1 and 1, -1 plus 1 by 2 is 0. So, this is also a weak solution. Let us look at this. In this case dxi by dy is this quantity -1 plus a by 2, -1 plus a by 2 and the average is also that -1 minus a divided by 2, which is precisely this. Here dxi by dy is 1 plus a by 2 and that is precisely the average 1 plus a by 2. Here xi y is 0, dxi by dy is 0. For this curve dxi by dy is 0 and that is also the average -a plus a by 2 is 0. So, here also RH condition is satisfied across all the 3 discontinuity curves. Let us look at the example 2, which is 1 and -1. This also has many weak solutions, this is one of them. Here dxi by dy is 0 because this equation x equal to xi of y equal to 0. Therefore, dxi by dy is 0 and that is the average of 1 and -1. So, RH condition is satisfied. Here it is 1 minus a by 2 and that is precisely dxi by dy. This is the xi of y, so dxi by dy. Here -1 plus a by 2 and that is dxi by dy. So, RH condition is satisfied across this line also. What about this line? Also because -a plus a by 2 is 0 and that is xi dash of y. Xi of y is 0, therefore, xi dash is also 0. So, RH condition is satisfied across all the 3 lines. Let us look at the example 3. Look at this. Here of course, there are many pieces, right. This is one line of discontinuity, this is another line, this is another line. Let us look at the top line, this line x equal to y plus 1 by 2. Okay. What is xi dash for this line? Half y by 2, right. Xi of y is y by 2 plus 1 by 2, derivative will be 1 by 2 and that is precisely the average 1 plus 0 by 2. So, across this line RH condition is satisfied. Let us check whether across this line RH condition is satisfied. Across this line 1 minus x by 1 minus y is nothing but 1 because on this line x is equal to y. So, therefore, 1 minus x by 1 minus x, u is 1 from this side, u is 1 from this side, therefore, average is 1 and that is also xi dash of y. Xi of y is 1, therefore, xi of y is y, therefore, xi dash of y is 1 Therefore, RH condition is satisfied here also. Now, let us look at this line x equal to 1. On this line x equal to 1, this u is 0, because it is 1 minus x by 1 minus y, x equal to 1 means it is 0 by 1 minus y. So, u is 0 this side, u is 0 this side. So, average is 0. Now, what about xi of y's derivative? Xi of y here is 1 and its derivative is 0. Therefore, RH condition is satisfied across all the 3 line segments. Now, the concept of entropy solutions, we are not going to study too much about it, but just to get some awareness. So, we saw that there are too many weak solutions. Is there a special one? Somehow we are longing for a unique solution. So, we saw that classical solutions may not exist for all t positive, even for smooth initial data. For Burger's equation we have seen. We relaxed the notion of solution to a weak solution, we did that. But we got too many solutions, too many weak solutions defined for all x in R and for all t positive, we just saw now. Thus, our notion of weak solution is too much relaxation. Can we find a good weak solution? This is where the notion of an entropy solution appears. Entropy solution is, people call it as a physically relevant solution. In examples of physical importance, they have introduced this entropy concept of entropy solution, and that is indeed a physically relevant solution. And even for a mathematical problems which are very far from applications, any entropy condition people call it a physically relevant solution, there is no physics behind that. Entropy solution is what is a desirable solution because it fixes some solution uniquely even in a mathematical problem. So, entropy solution is at most 1. That is how the notion gets developed. Okay. So, further discussion on entropy solutions may be found in the books by Bresson and also the book of Smaller that I have earlier referred to in the last class. So, with this we conclude the discussion of first order PDEs. So, what did we see in this lecture? How a notion of weak solution evolves, it was demonstrated. Minimum requirements that any reasonable notion of weak solution must satisfy, they were discussed. A notion of weak solution was developed for Burger's equation using a conservative form. A characterization for curves of discontinuity for piecewise smooth weak solutions was obtained, that was called Rankine-Hugoniot condition. Using the above condition, we identified some functions which are piecewise smooth solutions to Burger's equation, and in fact we have all the examples that we have seen, they are all weak solutions only, we found them. So, weak solutions are not unique in general, and thus one needs to impose more conditions on the notion of solution, so that the problem admits only one solution after this imposition of new rules. And this lecture is intended mainly to say that whatever initial conditions and solutions that we considered in 2.15 lecture, of course they are not classical solutions, but still they have some meaning and they can be given meaning in the sense of weak solutions, and further continuation is entropy solutions. Thank you.